Hello everyone, my name is Florian, PhD student at Ghent University, and this talk is centered around the question, are thermocouples lying to us? And in a slightly more extended version, this question becomes, are thermocouples lying to us about the adiabatic surface temperature in the fire decay and cooling phases? Now, for every surface in a compartment fire, we can write a general heat balance, which tells us that the total net heat flux onto a surface consists of a convective part and a radiative part. The convective part we can substitute with Newton's law of cooling. In the radiative part, we can say it is the difference between the incident heat flux and the emitted heat flux. And with a bit of imagination, we can also say that the incident heat flux comes from a source, which is a black body emitter at a certain temperature, Tr. If we compare this to the framework of the adiabatic surface temperature, we see that the heat balance formulation is very similar, but not exactly the same. The main difference is that in the adiabatic surface temperature framework, we do not distinguish between a gas temperature and a radiation temperature. We just have one temperature, the adiabatic surface temperature, which is going to cause the same total net heat flux as what we had before. The adiabatic surface temperature is usually based on fixed values for the convection coefficient and the effective emissivity, and these values are usually derived for the fully developed phase. But this leads to questions, because how do these assumptions perform in the fire decay and cooling phases? And two, can we use thermocouple data, the most widely available data, to validate such models in the fire decay and cooling phases? And to give an answer to this, we first need to understand the conditions that we will encounter in compartment fires. So after flashover, the first important phase that we encounter is the fully developed phase, which is characterized by an optically thick smoke at a high temperature. Basically, the smoke is a source of radiation, which means that the gas temperature and the radiation temperature are the same. And if in the framework of the adiabatic surface temperature, we would also be using correct values for the convection coefficient and the effective emissivity, that would also correspond to the adiabatic surface temperature. The second important phase is the pure cooling phase, which is characterized by the absence of smoke. The air inside the compartment is relatively cool because it's continuously refreshed and the linings are the dominant source of radiation. In this phase, the gas temperature and the radiation temperature are completely different. And in between those two phases, we have the decay phase, which is a transition phase going from one extreme to the other, just as the growth phase is also a transition phase before flashover. Now, to answer our two questions, we came up with a very simple setup in FDS. So we have a box geometry, which has some holes in the floor and the bottom to allow for flow of air and smoke. In the center, we have a thermocouple tree, but for the sake of representation, we're going to limit ourselves to the bottom one and the top one, which are at 10 centimeter distance from the surfaces respectively. And the scenario we're looking at, you could call it the onset of the decay phase, is a scenario in which we have a ceiling temperature of 1000 degrees Celsius, a floor temperature of 400 degrees Celsius, and a smoke that's initially optically very thick and also at a high temperature, the same temperature as the ceiling. What we want to demonstrate first is that as long as you're measuring with your thermocouple inside the smoke layer, that you're measuring the real gas temperature. So as soon as we start the simulation, due to buoyancy, the smoke layer or smoke flows out of the compartment and the smoke layer gradually moves upwards, which means that the area or the zone close to the floor gets into a optically thin environment sooner than the zone near the top of the compartment where the smoke layer will be present a longer time. In terms of temperatures, we're mainly interested in the difference between the thermocouple temperature and the local gas temperature, which you can see on the plot on the left-hand side of this slide. What we can see is that there is this phase where the difference is very close to zero, so where a thermocouple is basically just measuring the true gas temperature. And this phase takes longer as when you're closer to the ceiling, which makes sense because the environment near the ceiling remains in this optically thick state, thick smoke layer for a longer period of time. So this is a very clear indication that when you're measuring with your thermocouple in the smoke layer, that you're actually measuring the true gas temperature. And as we said before, if you're using for the fully developed phase correct values for the convection coefficient and the effective emissivity, you could potentially also be measuring the adiabatic surface temperature. But as soon as you go outside the smoke layer, you see that there are large differences between the thermocouple temperature and the local gas temperature, and those differences depend on your location within the compartment. With respect to the adiabatic surface temperature, I would like to highlight that there is an important difference between how we would measure it in an experiment with, for example, a plate thermometer, and how we apply it in calculations. If we're looking at experiments, we have changing conditions. Our temperatures change, flows change, and the resulting convection coefficient will also change. If we look at the way we use it in calculation, we just use a fixed value. And FDS actually allows you to compare the two. So the first one is using output quantity adiabatic surface temperature, and here you can see what the result would be for the ceiling and for the floor. If we plot also the adiabatic surface temperature gas, which is based on fixed values, you can see that they return slightly different results. So even with a plate thermometer, you would need to be very careful because it doesn't give you the correct result. And if we then compare thermocouple temperatures, you can see that they are completely different. Now, to conclude, we can say that thermocouple readings are affected by radiation according to their position within the compartment and the optical thickness of the smoke. Fixed values for convection coefficient and effective emissivity are incompatible with changing conditions, and thermocouple measurements cannot be used as a validation for the adiabatic surface temperature in the fire, decay, and cooling phases. And with this, I conclude my presentation. Thank you very much for your attention.